Now let's going on to the consideration for the intermediate state. Intermediate state is the strong magnetic field case in the type 1 superconductors in strong magnetic field. Before to describe for intermediate state, we should consider for the demagnetization factor. Let's consider for the thin rod superconductor, and it is a thin rod superconductor. The other one is the spherical superconductor. There are two superconductors. In this case, when we apply magnetic field and like this, and the applying magnetic field is in this case, then the field line can be straight. Even though we consider for the screening current, negative screening current, but anyway, in this case, that the magnetic field line can be straight. But in the spare case, when you apply magnetic field like this, magnetic field is deviating by the through the sample, and here, and therefore, we can say that the magnetic field effect is depending on the shape of the sample. And here in this case, the demagnetization factor we call eta. Demagnetization factor is equal to 0 in this case. In the spare case, the demagnetization factor is 1/3. And I will see the later. And the demagnetization factor depends on the sample shape, and I will say about that demagnetization factor in here, and it is characterized that HA over HC. HA is the applied magnetic field, and HC is a critical field for the superconducting transition from the normal state to the superconducting state, and also HC. Anyway, then the HA is always less than 1 because in order to have the superconducting state. If the applied magnetic field is greater than the critical current, it is not a superconductor, but it is an insulator. Therefore, it should have the less than 1. But in this case, we should consider only the demagnetization factor, and the demagnetization factor is a fractional value less than 1. And in this case, demagnetization factor equal to 0 for a thin cylinder. Or a plate, parallel field. This case is demagnetization factor equal to 0, and eta equal to 1/3 for a spare, and eta equal to 1/2 for a cylinder in a transverse field. It means that the superconducting sample is a cylinder, and the applying magnetic field is in this direction. like this. In this case, the magnetization factor is 1/2, and also eta equal to 1 for infinite slab, or the slab in a perpendicular field. In this case, the sample like this, it is an infinite slab, not infinite, just only the very long plate. And when we apply magnetic field, then the magnetic field should have like this. And the applied field, it is the magnetization factor equal to 1. Anyway, and what's the I should have a basic question. Why the superconducting state is appeared? The origin of superconducting state is that superconducting state is energetically favorable. It is very simple answer. Therefore, then the exact answer, not sophisticated, but the exact answer is that energy, superconducting state energy is more energetically favorable at low temperature. Therefore, let's consider for the free energy and the free energy consideration. And even though it is a phenomenological description, and it is reasonable. And let's consider for the total Helmholtz free energy. In normal state, Helmholtz free energy in normal state is that, and here Fn0 is that the free energy density in normal state in the absence of magnetic field, and also because small f means that it is the free energy density, and real free energy should multiply the volume. And also, because we apply the magnetic field on the sample in even the normal state, and let's consider for it is normal state, and we apply magnetic field, then because it is a normal state, and also like this, and also here HA is the applying magnetic field in the outside. We know the magnetic field energy density is that HA square over 8 pi in CGS unit, and also it is already known in electrostatics. Here is that the magnetic field energy inside a sample, because even the inside a sample, and there is a magnetic field in normal state. Also, the external, and the V external means that the external volume in the outside of the sample, and also it is magnetic field energy HA square over 8 pi. Here is Fm0 means that it is free energy density in normal state, in the absence of magnetic field. And it is outside the sample. Now it is a field energy. It is inside the sample. Inside the sample field energy. And when the sample becomes a superconducting state T less than Tc, when the superconducting state the superconducting free energy may have the Fs0. This is a superconducting free energy, in the absence of magnetic field, and also V is the magnetic, V is the volume. Because in the superconducting state, there is no magnetic field inside the sample. Therefore, the second term in the Fn, we should discard. Therefore, just only the outside external volume and HA square over 8 pi, it is the external magnetic field, because in superconducting state, there is no magnetic field energy inside the sample. And therefore, the energy difference, Fn minus Fs, it is energy difference. Let's subtract into side, and then V Fn0 minus Fs0, and also cancel with each other, and plus VHA square over 8 pi. And thermodynamic critical field, let's denote that in at critical field, and at critical field energy, Hc square over 8 pi, then exactly, and it is magnetic field energy difference, Fn0 minus Fs0. This is a thermodynamic case, and therefore we can write down as that V Hc square over 8 pi plus V HA square over 8 pi. And also at applying magnetic field is exactly identical to the critical field, and the normal state free energy minus superconducting state at the H equal to Hc is that V over Hc square over 4 pi. Therefore, we can say that why the superconducting state is energetically favorable is that the free energy of the superconducting state is energetically more favorable, and it is positive, and it means that the free energy, normal state free energy, and superconducting state free energy is lower than the normal state, and there is an energy gap between the normal state and the superconducting state. We call it as a superconducting energy gap, and it is at critical magnetic field. It is related. Superconducting energy gap is related to the critical magnetic field. Here they say that the transition from the superconducting to the normal state, free energy increases by this is free energy increase in the per unit volume. Then the energy source at the normal state is work against the back EMF induced as flux enter the sample. I mean that when there is a sample, and by applying magnetic field, then in the normal state, in the magnetic flux enters inside the sample, it means that the magnetic field energy is very high, but in superconducting state, the magnetic field energy inside the sample excluded, and therefore the free energy decrease. And therefore, the reason why the materials become the superconducting state is that materials favors to have the lower magnetic field energy when you apply magnetic field. In order to retain the zero magnetic field inside the sample and the superconducting current, superconducting generating, then the superconducting generation of a supercurrent, and for example, generating supercurrent in the outside to make a opposite direction, and is the induced EMF. Induced EMF is more energetically favorable in terms in the point of sample, and that's why it have the superconducting state. Now here, and anyway, and let's consider for the intermediate state in the flat slab. What's the here? Second. Intermediate state, flat slab. It is not a London theory. It is discussed by the Landau. Landau is famous physicist in Russian physicist. Landau consider for the infinite. Let's consider for the infinite superconducting slab like this. When you apply magnetic field, we can think about that at some region there is an impurities, and the normal state impurities can penetrate the magnetic field. But outside sample, and anyway, and the superconducting state is there is no magnetic field inside the sample, and therefore the magnetic field penetrating inside the sample at a certain normal state. We can think about that like this. Like this, and the magnetic field penetrating the sample in some cases like this. And anyway, let's assume that like this. And because from the, as I said, from the here the demagnetization factor for the infinite slab is 1, and therefore then we can think that the magnetic field may penetrate inside the sample, and this is a superconducting domain, and this is a normal state, and superconducting and normal state. And also here, let's write down as that here this region is a Dn. Write down like this, Dn, and this region ds. There is a domain, superconducting domain, and normal state domains. And here magnetic field, this is Hn, normal state magnetic field, and here Ba is the outside magnetic field. D is a sample thickness. Assume that magnetic field Ba is fixed at average value, and also H equal to 0 in superconducting region. And there is a fraction of the normal metal Ba over Hn. It is the fraction of normal metal. And here we let's find the scale and the shape of the superconducting and normal region. And here, in this case also, I say that the free energy, we compare with the free energy at the superconducting state and normal state, and free energy in nature, free energy should be minimized. And minimization of the free energy, and we can think about that how this intermediate state means that mixed state between the superconducting state and the normal state. In other words, intermediate state in the mixed state. And anyway, in the in order to calculate the intermediate state, let's calculate the surface free energy on the sample in the superconducting state and the normal state. And let's consider surface energy. Here F1, let the interface energy between the superconducting and normal domain. Interface energy between superconducting and normal domain. And F2 is that interface between sample and outside. For example, interface energy and superconducting and normal state, it is F1, and interface between the sample in the outside, and there are two outer surfaces. We call it is F2. It is a surface energy. Here we denote that interfacial energy density. Interfacial energy density, energy per unit area. Let's write down gamma, and it is proportional to the field energy, and the HC square over 8 pi is the magnetic field energy at the critical field, and the delta is a proportional constant. Here is delta, it is close to the psi minus lambda, and delta is the characteristic for the length difference between the coherence length and the penetration depth. As you know, then in type 1 superconductor, or the clean superconductor case, because the coherence length is larger than the penetration depth, therefore it is delta is positive, and in many cases delta is order of 0.1 to the 1 micrometer scale. But in type 2 superconductor, or the dirty superconductor, and penetration coherence length smaller than the penetration depth, and the interface energy delta is negative, and negative delta means that interface energy is negative, and they purport to generate many interfaces, and therefore in this case interface proliferate to gain negative surface energy, and therefore in type 2 superconductor we call there is a vortex. Vortex is a quantized magnetic field, and in order to have the many surfaces of the normal state and the superconducting domains, and how to maximize the interface energy that causes the magnetic field can divided by the magnetic quantum flux. We call it is vortex. Therefore, in type 2 superconductor and the quantized magnetic field penetrating to the sample, and the behavior of the vortex dynamics is very interesting topic in the superconducting materials. Here let's consider further two simple idea, and because two-dimensional infinite slab is very difficult to understand, and also let's assume that the Laminar motor in one-dimensional state is very easy to understand. Let's consider for Laminar motor. It is like this. It is like this. It is a periodic one-dimensional alternating at normal and superconducting periodic domains. 1D array of alternating normal and superconducting periodic domains. And the thickness and the normal domain thickness dn and the superconducting domain thickness ds. And the total domain is that the dn plus ds. It is a sample thickness. Here f1 means that f1 is the interfaces between the superconducting and normal state, and therefore it is interface energy, and here F1, here the area is a D, but in here there are two sides, therefore it is 2D, and D is that total sample length, and therefore 2D over capital D gamma is the interface energy. And here the interface energy we already said like this, and it is 2D over D and delta HC square 8 over 8 pi. It is it favors coarse structure, and in the in a clean superconductor, and delta is positive in clean superconductor, and F1 is that it favors coarse structure. It means that magnetic field can agglomerate with each other when the delta is positive, and in nature negative free energy is more energetically favorable. And F2 is that interface energy between the sample and the superconducting state. And in here, in F2 is that the interface energy between the sample and the outside, and therefore, and here F2 not limited to the only superconducting state, but also the normal state also. Therefore, F2 can be calculated, and the surface field energy of the normal state minus uniform field energy. It is surface field energy of normal state minus uniform field energy and normal state. And here let's denote that rho n is that volume fraction of normal state, it is volume fraction of normal state, and normal field energy Hn square over 8 pi is the normal state field energy, and rho n is the volume fraction of the normal state, and also minus in the uniform field energy. Field energy is that field energy is a BA square over 8 pi. Then it is a BA over 8 pi. BA square over 8 pi is the field energy in the outside, and here surface energy, it is a surface energy like this, and here surface energy, here we do not consider for the superconducting state, because at superconducting case there is no magnetic field. Therefore we cannot take into account that the superconducting surface, just only consider for the normal state field energy, and the minus uniform field energy on the outside. Then at the uniform magnetic field, applied magnetic field is that Hn and the rho n, it is natural, because at uniform magnetic field, because the magnetic field in the outside is originating from the normal state magnetic field, penetrating magnetic field from the normal state. Therefore, B is equal to rho n Hn is natural, and therefore it is that rho n Hn square over 8 pi minus rho n Hn square over 8 pi, then rho n Hn square over 8 pi, then 1 minus rho n, and here because rho n plus rho s equal to 1, and it is rho n rho s over 8 pi Hn square. And is excess energy density at the surface due to the domain structure. It is excess energy density at the surface due to domain structure. Here let's define that the healing length in this case, the n normal state and the superconducting state can be regarded as the connection as a parallel connection, and therefore n here dn and ds can be connected with a parallel connection, and therefore let's define that the healing length like this, and the 1 over L 1 over dn plus 1 over ds, it is a parallel composition, and also here dn means that the total domain and normal volume fraction, and plus ds means that the total domain and superconducting volume fraction, and therefore it is 1 over d and 1 over rho n plus 1 over rho s. In other words, it is 1 over d rho n rho s, and the rho n plus rho s is a 1 because from this, and therefore the healing length is like that, d rho n rho s. It is a healing length. Therefore, from this, and we can write down surface energy, excessive surface energy. Excessive surface energy is that the healing length is the surface, effective surface between the superconducting and the normal domain, and because there are two sides, and up and down two sides, therefore 2, and here rho n rho s 8 pi Hn square. In other words, and L equal to d rho n rho s 2d rho n rho s Hn square over 8 pi. We calculated for the F2 in here and the F1 in here. Let's copy. Therefore, F1 plus F2 is the total interface energy, and plus 8 pi 2d rho n rho s Hn square. Then here to find that domain structure, appropriate domain, periodic domain structure, and let's find that the minimum value for the, in order to find the minimum value of the domain structure, domain length scale, and let's derivative with Fourier energy with respect to the domain size. Then in this case, the second term is that 4 pi rho n rho s Hn square, and the first term minus 4 pi d square delta dhc square, and it should be 0 to find the minimum value. And from this, and the d can be write down, 4 pi can cancel with each other, and it is d equal to rho n rho s Hn d delta 1 square root and Hc. And also Hc is close to the Hn in typical, for the, if the applied magnetic field is close to Hn, there is an order of square root d delta over rho n rho s. For the Hc is close to Hn case. And the typical size of this domain wall thickness is proportional to the delta, and the delta, we remind that it is the difference between the coherence length and penetration depth. In clean superconductor, in type 1 superconductor, it is positive. Therefore, the effective domain structure, and from this calculation and experimentally, it is typically order of 100 micrometer scale, which is consistent with the experiment. Also, let's find that the critical magnetic field is important property to describe the superconducting state, and the Tc and Hc. Let's think about it here. Free energy, surface free energy. This is less first. Surface free energy and domain structure. And the second is that the critical field. In the intermediate state. The surface energy depresses the critical field in the intermediate state, Therefore, from this, and let's consider for the free energy density in intermediate state. The free energy density in the intermediate state from the above, the F, this F is not a Helmholtz free energy but interface energy. We should remind that F is not a free energy in this case, and therefore here the free energy density in the intermediate state Fi, then free energy density in the superconducting state at superconducting state, and also superconducting volume fraction rho s plus rho n and F S0. Anyway, and from here, and I'm sorry, Fn0 plus interface energy, and here, and the first term is that superconducting free energy, and second term is that normal state free energy, we know that the interface free energy is that this interface free energy F1 plus F2, the total F, and also for it is a density, and divided by the D, and because it is a free energy density, and also in the normal state free energy can be considered as superconducting free energy plus field energy. From the above, this one-dimensional laminar structure, and the normal state free energy is that superconducting state free energy plus and the field energy. Therefore, we can write down like this, and therefore let's denote again, and it's a rho s F S0 plus rho n. Superconducting state free energy is that F S0 and plus, and the critical field hc square over 8 pi, and the field energy is the hn square over 8 pi, and plus interface energy is that d over f1 plus f2 over d. Therefore, from this, and it is F S0 plus rho n hc square over 8 pi plus rho n hn square over 8 pi plus let's remind, okay, it is a total F. It should be divided by the small d. Therefore, it is 2 delta hc square over 8 pi, and also here is the d. D is that like this. 1 over d is a rho n rho s over square root d delta plus a pi d 2 pi rho n rho s hn square in times, and the d square root d delta over rho n, rho s. In the case it is not real, when Fy is minimum and Hn equal to Hc, the applied field at the critical field, and rho n is that Ba over Hc, because Hn is Hc. Therefore, from this, and Fi becomes Fs0 plus rho n Hc square over 8 pi plus rho n 1 over 8 pi. Hn is that Hn, here Hn is Hc. Hc is equal to Ba over rho n plus then when you calculate from the two terms, and also here 8 pi to Hc square rho n rho s, the first term is that square root d delta plus Hn is equal to Hc square, therefore plus d rho n rho s, rho n square and rho n, here rho n rho s and square root c square rho s. Okay. Rho n square plus square root d over delta. Anyway, here's also d delta of d square root d delta, and here is Hc square, like this. Okay. Same. And then it is when you write down, it is two, therefore it's a 4. Okay, we can summarize like this. And anyway, and here it is Fs0 plus rho n Hc square over 8 pi plus it's the square. It is 8 pi rho n Ba square plus 4 over 8 pi rho n rho s. Yeah, rho n is that BA over HC and rho S 1 minus rho n, and also square root delta over D. Yeah, it is a rho n and rho S. Okay. And also HC square. Then it is cancel HC. Yeah, okay. BAHC. Okay. And in order to have the minimum point for the normal volume fraction and the less derivative, let's have derivative with the apply to the rho n. Then HC square over 8 pi minus 8 pi rho n square BA square minus 4 delta over D HC BA over 8 pi should be equal to 0. Then BA square over 8 pi rho n square should have the HC square over 8 pi 1 minus 4 square root delta over D BA over HC. Therefore, rho n is the normal state volume fraction. It is the BA over HC 1 minus 4 square root delta over D BA over HC minus 1/2. Here in the critical field, means that the normal state becomes 1 and the total sample becomes a normal state, and therefore it is 1 equal to BA over HC and 1 minus 4 square root delta over D BA over HC to the minus 1/2. Then HC here 1 minus 4 square root delta over D BA over HC, and HC square is BA square. Therefore BA square plus 4HC 4HC square root delta over D BA minus HC square equal to 0. It is a second order equation, and therefore BA is that 1/2 minus 4HC square root delta over D plus minus square root B square 16 HC square delta over D minus 4AC plus 4HC square. Therefore, it is that HC, when we summarize the HC, then is the second term. Here is the we subtract the 4, we divide by the 4HC square. Therefore, square root 1 plus 4 delta over D minus 2 square root delta over D. Then it is critical field for the intermediate state. here in the HC intermediate state critical field can be write down HC and from the binomial theorem, and from the binomial theorem is that the 1 plus 2 delta over d minus 2 square root delta over d, and the d is the sample thickness, and the delta is that psi minus lambda, and d is the sample thickness, and therefore delta is very small and d is very large, and it is very small. Therefore we can exclude this term, and the HC1 for d is very larger than the delta. The HCI is close to HC 1 minus 2 square root delta over d, and it is a critical magnetic field at the intermediate state. Critical magnetic field at intermediate state is lower than HC, and here it is a final result. In the intermediate state in the one-dimensional laminar structure, and the critical magnetic field is the magnetic field that breaking the sample becomes a normal state, and in intermediate state the magnetic field is lower than the critical magnetic field. There's as much as this latter term. Therefore, and because for the finite delta means that the finite large coherence length comparing with the penetration depth, which is conventional in the type 1 superconductor, type 1 clean superconductor, and the critical magnetic field, there is an intermediate state. And the intermediate state means that a mixed state between the normal state and the superconducting state. It is natural to understand, and you can understand the feeling. And for infinite slab, for the HC breaks the superconducting state for the sample as a whole, but it intermediate state at the penetrating the normal state. This critical field at the intermediate stage should be lower than the critical field, because critical field is the magnetic field to destroy the superconducting state of the entire sample. It is natural to understand.